Hello. Right, today we're going to start by watching this video of someone quite amusing. You're going to like this man. It's going to make you smile, I think. I've watched it several times before. It's very informative. He is 11 minutes, but I think he's probably even more interesting than me, if there's such a thing. Give him a whirl. Please have a go. It is quite funny. I'll press play, but I don't think you want to go. Okay, hopefully you've watched that chap. If you haven't, you've been very naughty. There's a link again. Please watch him. He's quite good, amusing, and he goes over all these rules here. So to understand and use permissible row and column operations to find determinants easier. To be able to perform operations to change a matrix into a triangular one. He's showing you what one of those is. And to know how various linear operations affect the value of the determinant. He showed you that in a little table. We'll see it again in a minute. And to be able to factorize a matrix to find its determinant. So those are things we're going to do today. Right, I went over these, but here are the three elementary rows that you can perform on a matrix. You can swap columns or swap rows. You can multiply a row by a constant, so multiply a column by a constant. Or you could add a non-zero multiple of one row to another, or add a non-zero multiple of one column to another. Interchangeable columns and rows in those sentences. There is a definition box here. I'm not sure if I like this with saying M and N, but never mind. Pop group that. If matrix n is obtained from matrix M by swapping two rows, then the determinant of n is the same as the negative determinant of m. Just make those two n's, it makes more sense. But anyway, multiply one row or one column by constant k, then the determinant of n is the same as that number times the determinant of m. And then adding a multiple of one row to another, well, the determinants are equal then. Or easier to understand in this little table that he showed you in the video. If you interchange two rows, this changes the sign of the determinant. If you multiply a row by a constant, then the determinant is multiplied by that constant. Or if you added one multiple of one row to another row, then there is actually no change in the determinant. Triangular matrix. This is a square matrix in which either all the entries above the principal diagonal or all the entries below the principal diagonal are zero. So here's a principal diagonal, 161, underneath it, zeros. Principal diagonal, 187, above it, 0. So those are triangular matrices. One's an upper, one's a lower. Working out the determinant of these matrices is rather easier than the full matrices. We have so many zeros. In fact, I'm not sure if I showed you this video, it's a while since I watched it in full. In fact, the determinant is just of the principal diagonal. Let's see what that blank's meant to be. Lost my pen. It's a surprise, is it? Just a sec. No. Oh, there it is, on the floor. Hope you're making notes, Seb, today. How rude of you not to make my notes. Anyway, determinant of matrix A, that's why we've got the straight brackets around it. So that's if we were multiplying, we take the bottom row. Let's do it on the bottom row, it'll be easier then. So we use there bits plus minus, plus minus, plus minus, plus minus, plus. So I'll go 0 times the determinant of those four, which would be 16 take 6, plus 0 times the determinant of 1 times 4 take 0. So this is pretty stupid, isn't it? Anyway, we're putting zeros in, and then 1 So should that be naught? That should have been a minus. Minus naught times that. And then make a difference, is it plus 1 times the determinant of cross and cross 6 take nothing. And all that works out to be 6. So what is that? Determinant of, if you think of the diagonal there, if you times 1 times 6 times 1, you get 6. So it's, in fact, the determinant is just the product of the principal diagonal. So we know the answer to be, times those together, 5, 6, 7, 8. So that's 56, isn't it? 56 times 1 is 56. So that's the answer. And if you wanted to prove it to yourself, use the top row to expand it on. 1 times determinant of 8 times 7, take away 0 times 9, and the rest of them are 0, 0, because you're multiplying out on the top line. So answer is 56, yes. Super. Fun. Factorizing matrices, that's pulling out common factors. You can pull out factors of rows, factors of columns. Must be common to every row or every column to take it out. So here, hopefully you can see, you can take an x. If we think of that, I'll put that in a bracket like that. You'll see in a minute. So take an x out of these, you get 1x x squared. And make these fancy colours. So take y out of the next column. And z out of the last column. It says factorise completely. So ideally we want like the triangular matrix. So what we could do here, we could do column 2 take column 1 and column 3 take column 1. So column 1 stays the same. Column 2, we take away column 1 from it, so that becomes a 0. Y take x, and y squared take x squared. Similarly with this one, column 3 to column 1, no. Z take x, z squared take x squared. Alright, so I've got noughts there. We'd like a nought there as well, really. But anyway, if we can see some things, hopefully to factorise, can we? Ooh, it's very tricky to spot this one. Here, middle column, that's the difference of 2 squares, isn't it? So you can take y take x out, because y take x times nothing is nothing. So you can factorise this time out of column 2. I should have left the, sorry, x, y, z should still be there. So not just factorising x, y, z. But at the middle column, we can take out y take x. Now at the end column, you can actually take out z take x. And then your matrix looks a bit like this. We haven't changed the first one. But now I'm changing this, aren't I? 0, 1, and that's difference of 2 squares, so it's actually y plus x. And this one's 0, 1, and z plus x. Now if we triangular matrix in it, that needs to be a 0 to make it an upper triangle, well, one of them anyway. So we need to do column 3 take column 2 would make that a 0, wouldn't it? Ooh, magic, magic. So our answer will be, oh gosh, I'm going to scratch this in. And then do this thing, I'm going to squash it in. 1x x squared, 0, 1, y plus x. And here we're going to get 0, 1 take 1, nothing. And we're going to have z take x, take away y plus x. So that actually ends up as z, the x go, don't they? And take away y. Slash that on. Now it's easy to do the determinant. Those should be in straight brackets, shouldn't they? Know what you mean? Right, so the determinant is x, y, z. Y take x, Z take X, and determinant of that thing expanding on that one there will be that times that take nothing times something. So it ends up 1 times Z take Y. And then you can just forget the 1 if you want. Let's write that one more time. If you just haven't had enough, it's X, Y, Z. Don't need the bracket around that. Fascinating, eh? That's got you tickled. Right. Oh, we had a bit of space for that. You could spread that out if you wanted. Right, this one. Show that that's a factor. We can't pull that out straight away, can we? So we're going to have to do something. Remember, we're aiming to get triangular matrix. So what might be an idea here is do it with rows. Let's do row 2, take row 1, row 3, take row 1, then we'll get some notes, won't we? So that will be equal to, because it won't affect the matrix, 1, A, B, C, 0, B, take A, and AC take BC, another pop group. 0, what was ACDC, wasn't it? No, I don't know if I'm too young to know that. Right, bottom row take top row. A, B, take B, C. Now, if you might be able to spot how they're going to get that B take A out, A take B out. Just write that one more time by switching the algebra about it. So, right, if I write that as minus lots of A take B, you'll see it then. This one will pull out a common factor of C and you get A take B in a bracket. This one, take a minus out, just while we're there, A take C, and then in this bracket, if we pull out the common factor of a B, we'll have in there, blast tooth, still got tooth here, A take C. And now you can see this row has got a common factor and that row has got a common factor, so let's pull those out. And then we can write, oh, no, that's not meant to equal, it's like a times. 1, A, B, C, 0, minus 1, and C, 0, minus 1, and B. You could multiply out the matrix from there, but if we're doing for proper zeros, we'll get rid of that bottom one. So to get that, we need to do row 3. Change row 3 to row 3, take row 2. I think that'll work. So that stays the same. Oh, we should be doing it as row, shouldn't I? Sorry, that row stays the same. Middle row stays the same. But bottom row, I'm hiding some of it. That, take that. 0. And that must B take C. So now multiplying out that matrix will give us, if you do it on the B take C, will be B take C times the determinant of these ones. So that's minus 1, take away nothing times A, nothing. So the answer just ends up as being C take B. But as I've said, I've been naughty in the past. And there, I've forgotten to write that there, haven't I? So it should have been A, B, ooh, do it small, A minus B, and A minus C times this thing. And then here, let's try and cheat a bit. We should have had, before I wrote that, we should have had that A take B and A take C in there. So times 0 by minus 1 ends up with our final answer. I'll do it in blue. A take B, A take C, multiply that through by -1, you'll end up with C take B. Fascinating. These really do amuse some people. Oh, another question. Thank God it's a 2 by 2. Right, find the determinant of this matrix. Well, you say you could expand it all and do it, but it's better if you factorise first, perhaps. So, factorise. Let's just take some common factors of that. So, determinant, put this thingy bracket. We'll call x difference of 2 squares. We should know that, shouldn't we? This one, does it factorise? I hope so. Bottom one, does it factorise? Well, yes, it does. That's a difference of 2 squares again, isn't it? So look, we can factorise something out now. So in the 2 columns, x plus 2 comes out the first column, and x take 3 comes out the second column. And we're left with like that. Now you could multiply that out if you fancied, or you can do, let's do, show off our skills now. Let's do column 1 take column 2 and see what that gives us. So we're still on. That doesn't change the determinant, does it? So we've still got x plus 2, x take 3, but determinant of now, column 1 take column 2, the x's go, and you're left with -3. X's go, you're left with -4, and column 2 staying the same. Now maybe go for, make it not, just let's multiply it out. So we've got x plus 2, x take 3, and the determinant of that you end up with -3 times those, so that's -3x minus 9. Take away that times that, so it ends up with +4x plus 4. And then all that comes to x plus 2, x take 3, and x take 5. So that's pot I. Pot I. For what makes the matrix singular? Well, singular means the determinant is 0. And if it's 0, then remember it doesn't have an inverse. Wow, yes, great. So if you make all that equal to 0, then what values of x can make that equal to 0? We should know that then x would have to equal either -2, 3, or 5. And then we've answered it. Super. Okay, I think it's a bit of your turn now, thank goodness. These can take ages, but you get a real buzz when you get it right. Okay, it's your turn. Can you fully factorise that? Pause the video and have a go. Factorise the determinant of that thing. So try and make it triangular and have a buzz. Please pause. Okay, unpaused. Here's a bit of solutions. And to fully diagonalise it. Oh gosh, I'm in the way. Get zeros there. I don't know if you can see what's under there. You probably can't, but maybe you can work it out from what I've done down here. I don't think you needed that bit for that. Did it ask you to find x's? No, oh, never mind. Right, next one. Have another go if you didn't get that. Pause the video now and see if you can factorise that thing. Okay, unpaused. Here come the answers. Diagonalise it, and there's the answer. Wow. Is there any more? Yeah, tricky one. Can you get any trickier? Well, there you are with trig. Let's hope you're good. Have a go with that one. Find in factor form the determinant of the matrix A. Find the values of theta for which det A equals 0. So you can see you're in radians when you go 0 to 2 pi. That's like 0 to 360 if you remember. Okay, pause. And now unpaused, here come answers. Must have been drinking. Triangulise, that's only Ribena. Hiding a bit of the solution there, and it comes out as that. Then it says, find the values for which the determinant is 0, so you'd equal that to 0, and try and solve it for cos and sine, well, for theta. Don't know who did trig with you, depends on who did trig, whether you understand that cast diagram or not. But here come the answers, however you want to do them, whether it's using your calculator or whatever. There they are. Did you get it? Let's hope. Right, whiteboard's another one. It says here, find the determinant of this thing, which is correct solution. Identify the errors made in the incorrect solution. So pause the video and have a think, or don't pause actually, because I'm just going to go and check my tea. I'll just give you time to think. All right, haven't you ever think about it? Squirrels come to say hi. Hello. Right. Find the terms of that thing, which was the correct solution. Spot the errors. Hopefully you spotted them. Have got to write it. That was the error here. They should not have pulled x out, should they? Or should they? No, they should have pulled x out 3 times, haven't they? So it's x times 3. Right, it's 3 x's. So x to the 3, that's what they should have got there. Ooh, put that in. Should have been x to the 3. And so that should have been x to the 3. That should have been 2x3. That's right now. Number 2. Hopefully you found that one was correct. Number 3, what went wrong here? They multiplied it out. That's good. That's not good, is it? There. That should have been a minus. Oh, squirrel. Come on, sweetheart. And then it works out at x plus that, doesn't it, when you sort that out? And then it's here, it's 2x to the 3. That was the error there. Right, okay. That's last bit now. Ooh, flashy bit. That's great. Using the determinant to calculate the vector product. Oh, we did that, didn't we? We've done vectors. There's a new vector song on my website if you want to do I, J and K. You'll see it on the video anyway. But anyway, we saw vector chapter, did the cross product of two vectors with that formula, or you could have set them out as determinant of that. So here it says on the example 4, last one before I shut up, I think. Those are the two vectors, find A cross B, so if you just practice that again. So we'd write that as J and K. You'll enjoy that, sorry, if you go to my YouTube. And then we've got first vector A, so that's 1, 2, minus 4. And here we've got minus 6, 3, and 1. Oh, we're just crossing them, yeah. We're crossing them, so that should be curly bracket, no, we're not determinant. Right, so how we work that out, if you remember, it's I, and then you, and 2 takes plus 12, and it's minus J, and then 1 take 24, I can do maths, and then plus K, and 3 add 12. Ooh, tricky stuff. So that gives us 14i plus 23j and plus 15k. And if you like me and don't like that sort of thing, like component form, you can write it as vector form. 14, 23, 15. Super dupe. Check it with a calculator, with the cross product thing if you've got one, or you can be bothered. Right, what's next? Anything or nothing? I don't think there is anything. Oh yes, it's an exercise for you. Woohoo! I'll write it on the thing. There might be too many questions. Just do, you know, a certain amount of time on them, rather than every question that I set. Just do what you think is an appropriate amount of time, maybe half an hour. Well, if you get into them, please spend more. You might enjoy them. This last slide, just back to that funny little man in the green suit, if you remember him. He does some more. The Kramer rule, does something called the Kramer rule. Quite a new course, but it's still interesting and it still can be relevant to what we do next lesson. So if you enjoyed him the first time, which I'm sure you did, and I think that's another one of his links. So another one of his little sessions, and he'll wear another funny little suit. So I hope you enjoy that. And catch you again in a week or so's time, whatever Carrie Ann decides what we're up to. But yeah, catch you soon. Bye.